Already?
I like it. This one's good. M10 is all about the role of enzymes. So, in terms of energy. So, enzymes, I don't know the specific wording, let me just check. I might get it wrong. Okay, enzymes increase reaction rates by lowering activation energy. I've actually got a pretty cool simulation to show you coming up, but it allows you to use a bow and fire molecules at each other. Okay, so I'm sure you like that. So basically, what we need to understand is very simple. You can teach this whole piece of information in one graph. Okay? Within our system, just for the record, Luke was on his phone, Mr. Rumsby. Okay. In our system, our molecules have energy. Why do they have energy again, Ryan?
Why do molecules have energy?
Yep.
We need energy for function, growth.
What gives them that initial energy? Sort of. So sometimes there's energy trapped in their bonds, so they have energy. But what about what makes them move around?
Kinetic energy.
Kinetic energy. So all these molecules within our system, we call it sort of free energy. There's kinetic energy around, which is making them move. They're going to collide, and if they have enough energy, they may react.
Gibbs free energy.
So what we look at on the y-axis, we'll call this free energy, which is energy within our system. What this refers to is not too important. I think you do a little bit of this actually in chemistry.
Gibbs free energy.
Yeah.
So,
we have initial energy at this point of our molecules. Okay? So molecule A and molecule B, say. These molecules need to reach a certain level to react. Okay? So they have a reaction threshold. If the molecules can't reach this particular height of energy, so this particular level of energy, they won't react. So they'll stay as molecule A and molecule B. They won't become molecule C or say molecule C and D. So they're stuck. So what might happen is we might have a collision between A and B. We get initial bit of energy as they collide, the energies combine, but we can't reach our reaction threshold. Therefore we get no reaction. Okay, again they collide, again no reaction. So what's the role that enzymes play?
lowering the threshold.
Lowering the threshold, excellent, Nick.
We learned
Great
this
job.
yesterday. We learned this yesterday.
Okay, so we actually lower the threshold. So let's say it's from this position, we'll call that time. From this position here, we've added our enzyme. What that does is now makes the reaction threshold, or the activation energy, now at this level. So now when we have our molecules interacting, we can meet our activation energy and then react. And we're going to produce, so we might have A and B here, now they react to produce C. Okay, so the distance between here and here is our activation energy, so that's the energy that we require. The difference between this one and this one is the presence of an enzyme. Okay? So with an enzyme, the activation energy becomes lower, and therefore our molecules are more likely to reach that threshold and then react and produce C.
What was that distance again? Distance from reaction threshold to activation. I mean,
This is, the difference in here is either with or without an enzyme. So this is the reaction activation energy with or without an enzyme. Okay? So sometimes it's drawn a little bit differently, and I'll show you that in a sec. This is our output of energy. So we're below. So this would be a exothermic reaction. We're releasing energy. So if you think about your extremely old crack where you burnt some magnesium, that magnesium gave off a lot of light and a lot of heat, but we needed an initial source of energy to get that going. Okay, so all reactions need a little bit of energy to get going. Some either draw in more energy, which would be an endothermic reaction. Others are going to give off energy, which is an exothermic reaction. Any questions with that so far?
What was that A plus B thing there?
So these are our molecules.
Yeah.
Molecule A plus
Yeah.
molecule B react together to form molecule C.
Yeah.
So we've got normal energy, activation energy with the enzyme. Therefore, we're going to be able to reach that threshold, react, and then we get an output of energy. Okay? We could also draw it like this, and hopefully Zach can see it. So this is energy again. This is our initial free energy. So you could draw it like this. Okay, so now instead of just drawing it like this, I've drawn it with two different curves. So this is in black, A plus B without an enzyme. And this is A plus B with enzyme.
what's the first dashed line?
So that's the initial energy of the molecules. Okay, I know unfortunately the black text is not great, but can everyone see the difference there? Okay, so without an enzyme we have to reach this level of activation energy before reacting. With the enzyme we have to reach this level of activation energy and then we'll react. So the difference between these two is the lowering of the activation energy. Okay, so we just lower the activation energy. What I want you to notice here is the output of energy is the same. Yes, Darcy?
What's the line that's between the activation energy and the other dotted line? On the other one?
This one? So this is the height of the activation energy required with our enzyme. This is the height of the activation energy required without the enzyme.
There's a little arrow.
And this one here?
Yeah.
This is the distance between what they start with and what they need to react. So this distance here, or this height, is called the activation energy. So you'll notice that it is bigger without the enzyme compared to with the enzyme. And that sort of you can see a little bit easier with this one. If you look in the notes that I've given you for with the PowerPoint, you'll see a really good diagram on slide 7. So in an exam or a test question, you'll have to be able to label these different parts. So we'll go, what is the dotted line represented by A represent? So what does the dotted line A represent? And you have to go, this is the activation energy without an enzyme. what does the dotted line B represent? This is the activation energy with an enzyme. Okay. What does the dotted line, the distance between the dotted line and C represent? That's the output of energy, or the energy output after the reaction. So even with the enzyme, what we produce isn't any different. It's the same. It just means it's more likely to happen.
Oh, come on.
Okay, does Zach even hear what I asked of you?
Did you, Zach?
Yeah, Zach.
He's probably playing along at home and he's done his own graph and it looks exactly right. So this is a reaction where we're adding energy and not releasing energy from our system. Is that right, Joe? Beautiful. Make sure I don't say last names because then it gets a bit stalky. Did I? Sorry, Matt. Yeah, some stalkers. Place annoyed as well.
No, I was just listening to you say.
Okay. Alrighty. So we're going to have a height, an activation height. Let's say we do it without the enzyme. So we're going to have a activation energy. So that's the energy that we require for a reaction to occur. So what we're going to see is that.
See?
Okay. So now we've
It
got.
doesn't touch the line.
Yeah, it's like
We've now got energy stored in our product that's above our original energy. Okay, so we have now potential energy, chemical potential energy stored in the bonds of that molecule. Okay, so when we build molecules up, we're storing energy. When we break molecules down, we're releasing that stored energy. So if we have it enzyme mediated, so we call that activation energy. If we have an enzyme that's mediating this reaction, what do you think that might look like? Jonathan?
The activation energy will be lower.
Okay.
But the final product will still be above the initial energy.
Beautiful. So it's going to look like that. Or it might even get up there quicker, so it might be something here. Okay. So the activation energy required to store that energy in the product is reduced, but the energy that's stored is still the same.
Yes. I don't know if this will make sense or not, but wouldn't the required energy of one with the enzyme and without the enzyme go at the same rate, but then the one with the enzyme would occur quicker? So you know what I mean. So in terms of the graph, I don't know.
Yeah, I understand what you're saying. So you expect this to be the same, but to occur
Yes,
faster?
occur faster. Is that how it works? Because it's kind of requiring the same.
It may even occur quicker because we're going to have better orientation. So therefore the chances of reacting are going to occur quicker.
Yeah.
And then it's going to stress those bonds to make new bonds, so that's going to be faster. So what I would presume is that it would reach the activation energy quicker and produce the product quicker as well. Okay, but if anyone finds anything to the contrary, please let me know. Alright, that's it for that. I've got a video to show on the screen. So I'll wrap this up.